Welcome. In this video, we're going to talk through part 2 of periodic trends. We're going to cover some things that we did not yet cover in class today. And here are some of the textbook references where you can find this in your book. So it's mainly the end of chapter 8, and part of it's in chapter 9. So the first thing we're going to talk about is electron affinity. And here's a description. So electron affinity is the energy change associated with gaining an electron. So it's basically the opposite of ionization energy. And you can see some examples down here. In ionization energy, an atom loses an electron. With electron affinity, you're looking at an atom gaining an electron to form a negative ion. And if you look up here on this table, you'll see the electron affinity values are often negative. So here's a side-by-side comparison. Ionization energy is the energy required to remove an electron to form a cation, positive ion. Electron affinity is the energy released or required to add an electron and form an anion. So again, they're kind of the opposites. And something that you will notice is ionization energies are always positive. It always takes energy to remove an electron from an atom because you're having to overcome the attraction of that electron to the nucleus. Electron affinity could be negative or positive. So a lot of times electron affinity is actually negative. So adding an electron to an atom will actually release energy. So when those electrons get close to the nucleus, that's actually a lower energy position. So energy is released. So that's another important difference as well. So again, ionization energies are always positive. Electron affinities can be positive or negative, but they're usually negative. The major exception will be the noble gases. So if you look at this table here, you can see the noble gases have positive electron affinities, and so do a few other elements like beryllium and magnesium. And that's because since their outer shells are full already, to add an electron to one of these elements, you'd actually have to go up into a higher shell, and that would actually require energy. Electronegativity, it's the tendency for an atom to attract electrons to it when chemically bonded to another atom. And here's a visual of what this looks like. We'll talk about this more in Unit 2 with bonding, but here's a little visual for now. When hydrogen and fluorine form a covalent bond, they share electrons. It's represented by this electron cloud. Fluorine has a greater electronegativity than hydrogen does. As a result, the electrons are kind of spend more of their time on the fluorine side of this bond. So you see you got a greater electron cloud over the fluorine than the hydrogen. And we'll notice the trend in electronegativity follows the same pattern as our trend in first ionization energy. So over here on the upper right, where you have elements with relatively, large effective nuclear charges, they tend to have large first ionization energies. They also will have large electronegativities. So fluorine's nucleus is very attractive. It also has a small number of shells, so its electrons are closer to the nucleus. So those two things make its electrons more attracted. Over down here, like with francium, it's got a small effective nuclear charge, that's +1, and its electrons are in like shell 7. So those electrons are relatively further away, weakly attracted, so it's going to have a lower first ionization energy and a lower electronegativity. So those two things will follow the same pattern. Here's a visual of this. The electronegativity values are different from your ionization energy values because ionization energies are given in units of like kilojoules. The electronegativity scale is a unitless number. It's just a 0 to 4 scale, 4 being defined as the greatest electronegativity. So notice how fluorine over here is 4. So there are no units with this number. It's just like a comparative value there. Metallic character. So you want to be familiar with where the metals and nonmetals are located on the periodic table, and be aware that this is a spectrum. You can be more or less metallic in character. So the elements down here on the bottom left, we think of them as being very metallic in character. As we move this way, we become less metallic. Then over here, where the metalloids, where they're kind of in between, they're maybe somewhat metallic in character, but somewhat not. And then over here on the top right, you get your nonmetals. So you can also think about periodic trends in metallic character as well. All right, now let's talk about successive ionization energies. So we started out by thinking about the first ionization energy, which is the energy to remove one electron from a neutral atom. We have these things that we call successive ionization energies, which would be if, well, what if we took a second electron away from that same atom? Or what if we took a third electron away from that same atom? What we notice here is that each successive ionization energy is going to get harder. So the energy required to remove one electron from sodium is 496. And that's in kilojoules per mole. If I wanted to remove a second electron from sodium, notice how I would have to take it here from the 2p, and that second electron would take 4,560 kilojoules, so about 10 times as much energy. So they're going to get successively harder to remove those electrons. And if you take a look at this table, notice how it's color-coded. The blue values are the valence electrons, and the red values are for core electrons. And what you might notice is when you start removing core electrons, they become much, much harder to remove. Like in that previous example, we saw that to remove the first electron from sodium only took 496 kilojoules of energy. The second electron, which is in a closer shell, would take 10 times that energy, so like 4,560. It takes way more energy to remove a core electron. And that's because, going back to Coulomb's law, right? So force is proportional to charge over distance. Those core electrons are a lot closer to the nucleus. And we're also reducing the number of shielding electrons. Like those core electrons have fewer shielding electrons in between it and the nucleus. So you'll also find your effective charge goes up as well. So let's kind of draw this out actually here. So if you're looking at sodium, so again, we've got your, 2p here, and then you've got your 3s here. So the first ionization energy would be the energy to remove this electron right here. The second ionization energy would be the energy to remove this right here. So the second one's much higher. Notice with magnesium, what's different here is magnesium has 2 valence electrons in the 3s. So it's got a different configuration here. Let's draw out. So for magnesium, the first ionization energy is removing from the 3s. That's similar to sodium. But the second ionization energy, that second electron, will also come from the 3s. So notice how magnesium's second ionization energy is much smaller than sodium's is, because magnesium's second electron is still coming from the third shell, whereas sodium's second electron is now being taken from the second shell. So when you drop down to a lower shell, those lower shell electrons become much harder to remove from the nucleus. Sorry, they become much harder to remove from the atom. Okay, because they're more attracted to the nucleus. All right, so we can, using that information, we can actually analyze some data sets and figure out from these successive ionization energies how many valence electrons a substance has. So if we look over here at substance A, we're looking at its ionization energies. Notice how, it always gets harder. Okay, second's harder than first, third's harder than second. But as you go up here between the fourth and the fifth, wow, the fifth is so much harder than the fourth electron is to remove. So what that tells us, so there's a big change in how difficult it is to remove the fifth electron versus the fourth electron. That tells us that these 4 electrons must be further out. They must be on your valence shell. So that tells us that A has 4 valence electrons. I just had a deer walk by my window. Okay, cool. So if you look down here at element B, same kind of thing. We can say, where is there a big jump? Well, it looks like the second electron's twice as hard to remove as the first, but the third is 4 times as hard. So that seems like there's a big jump between the second and third ionization energy. So that tells us there's 2 valence electrons in our element B. So this one has 4 valence, this one has 2 valence. So we can use these successive ionization energies to figure out how many valence electrons something has. So a related topic would be looking at the radius of ions. Since we're talking about atomic radii, let's talk about ionic radii as well. And if you compare the radius of an element with its ion, you're going to notice some things. So first, let's look over here at the cations, these positive ions on the left. You should notice for all of these that the cation is much smaller than the neutral atom. And if you look at the electron configurations, we can see why. So lithium is 1s2, 2s1. When it forms an ion, it's going to lose its valence electrons. So the lithium ion is just 1s2. So it's lost its entire valence shell. And that is a pattern you will notice with all of these metal ions, is that these cations will be much smaller than the neutral version because they've lost a shell. Over here on the right, if you're looking at your anions, you will notice that anions tend to be larger than the neutral atom. And if you compare their electron configurations, you'll notice they have the same number of shells. So it's not because we gained or lost a shell here. What we have is with oxygens 1s2, 2s2, 2p4. Oxygen with a -2 charge is 1s2, 2s2, 2p6. So they all have electrons in the 2p. And they're both oxygen, so they both have 8 protons in the nucleus. So the number of shells are the same, the protons in the nucleus are the same. The only difference is how many electrons are in that subshell. So notice how the oxygen ion has 2 extra electrons in its subshell. And remember, electrons are negative. So if you put electrons near each other, they are going to repel because like charges repel. So anions tend to be larger than the neutral atom because of that extra electron-electron repulsion. So we got the same number of protons, but we got more electrons repelling each other. So they're going to repel each other. They're going to spread out. That electron cloud is going to be a little bit bigger. Another thing you can think about with ions is comparing what we call an isoelectronic series. So isoelectronic is when you have two substances that have the same electron configuration, and you can get this when you have ions. So for example, if we look at this series with sulfur, chloride, potassium, calcium, they are all isoelectronic with argon. They all have 18 electrons. So they'll all have the exact same electron configuration. So it's, 1s2, 2s2, 2p6, 3s2, 3p6. What's different, though, is the number of protons that are in their nucleus. So what we notice is sulfur has the smallest number of protons, so it's got the largest radius. Calcium has the largest number of protons. It's got the smallest radius. So if you think about your nucleus over here, let's draw, whoops. Okay, if we draw a comparison over here on this side, calcium's got a nuclear charge of plus 20, sulfur's got a nuclear charge of plus 16. Calcium is going to pull those electrons in tighter. So these electrons are going to be more attracted to calcium's nucleus than they are over here to sulfur's nucleus. So you're going to end up with the smaller radius, even though we have the same number of shells. They all have 3 shells, but calcium's nucleus is more attractive. So it's going to pull in those third shell electrons a little bit closer. So it'll be smaller. Okay, I just want to point out some things about noble gases because they're kind of interesting and different. They have completely filled S&P subshells. They end up with the highest ionization energy because they're over there on the right. So they've got the, greatest effective nuclear charge. They don't tend to accept extra electrons. They've got a positive electron affinity because they don't really want extra electrons because their shells are filled already. And we typically say that their electronegativity values are undefined. So you might notice on our table with electronegativity values, the noble gases just get left off, and that's because they don't typically form bonds. And electronegativity has to do with what atoms do when they form bonds. So if you don't really form bonds, we don't really have an electronegativity value. Okay, so last thing I want to talk about is some exceptions to the trends that we observe here. So like if you look at this graph with first ionization energy, we notice that as we go across the row, the effective nuclear charge is increasing and your valence electrons are in the same shell. So in general, we see the first ionization energy is going to increase, right? But you might notice that there are some exceptions. Like right here, we go from 801, 1086, 1402, and then there's this dip when you go from nitrogen to oxygen. Or as you go right here from beryllium to boron, there's actually a little bit of a dip. So those are some exceptions to this general trend. So in general, it increases going across a row, but there's some exceptions. We want to be able to explain why we see these exceptions. And a good way to do it is to look at the orbital diagram of the elements we're comparing. So like, let's look at nitrogen and oxygen, for example. Nitrogen has 7 protons in its nucleus. Oxygen has 8 protons in its nucleus. They both have these core, it's kind of like same core electrons in here. They both have 2 core electrons in the 1s. So you would expect oxygen's electrons to be more attracted than nitrogen's. So oxygen's electrons should be harder to remove. But if you look at this data, they're actually easier to remove. It only takes 1,300 kilojoules instead of 1,400. So what is happening here? Well, if we look at their orbital diagrams, we'll notice that a difference between them is that oxygen has some electrons paired up, whereas nitrogen does not. And remember, electrons are negative, right? So if we put 2 electrons next to each other, like charges repel, so they are going to repel each other. So in oxygen, since we have 2 electrons in occupying the same orbital, we have a little bit of electron repulsion here. So we've got some electron repulsion because we have 2 electrons in the same orbital. And that repulsion makes those electrons easier to remove than we might otherwise expect. So we'd expect oxygen to have a greater ionization energy because it's got a greater effective nuclear charge, but it turns out it's actually got a little lower ionization energy, and that's due to that extra repulsion caused by 2 electrons being in the same orbital together. Okay, so it's just a way, these exceptions, you do not have to memorize them, but if you are, presented with an exception, you might be asked to come up with a reason why. Like maybe they would give you this data and say oxygen's first ionization energy is actually a little lower than nitrogen's. Why do you think that is? So then you want to go back to your knowledge of atomic structure, think about the electron configuration, the orbital diagram, keep in mind that opposites attract, like charges repel, and you want to try and come up with an explanation for that. Another example of an exception, and this is from an old AP exam, why is boron's first ionization energy smaller than beryllium? I would expect boron's ionization energy to be higher, but here's another little exception. It's a dip in the trend here. What's happening when you compare boron and beryllium is they both have electrons in the second shell, but it turns out boron's valence electrons are in the 2p subshell, whereas beryllium's are in the 2s. And in general, we think of 2s and 2p as all being in shell 2, it's all the same. But in reality, 2p is actually a little bit further away from the nucleus than the 2s is. So that 2p electron is a little bit easier to remove than we might otherwise expect it to be. Okay, so even though boron has more protons than beryllium, since that 2p electron is a little bit further away from the nucleus than the 2s is, it's actually a little easier to remove this electron. So those are some examples of some exceptions. Again, you don't have to memorize them. You just might need to use your knowledge of atomic structure to give a possible explanation for why we might see these exceptions that we talked about right here. All right, let me know if you have any questions, and thanks for watching.